Hi, I'm Lee McCuller. I'm a professor at Caltech who works on the LIGO gravitational wave observatories. And I want to tell you today about a new technique that we're using called frequency-dependent quantum squeezing. So this is an exciting technique that we use in order to manipulate the uncertainty from quantum mechanics in light in order to make more and more precise measurements with our instruments. So to explain, let me first tell you a little bit about LIGO. LIGO uses lasers that bounce off of large, heavy mirrors to measure tiny ripples in space-time. These are gravitational waves. So these ripples cause the large mirrors of LIGO to move. They actually move a distance that is 10,000 trillion times smaller than a human hair. These signals are so small and these motions that we're trying to detect are so tiny that LIGO ends up limited by the laws of quantum physics in the precision that it can make its measurements. Quantum mechanics says that there is uncertainty in all physical objects. For LIGO, good examples are there's uncertainty in various aspects of the light that we use to measure, and there's uncertainty in the positions of the mirrors in the first place. So, beginning in 2019, we began using a technology called quantum squeezing to enhance LIGO. Quantum squeezing modifies or manipulates the uncertainty of the light. Light is a wave that we use to measure, and it has two major properties. It has the amplitude, and it has the phase. So the phase is like where the crest of the wave is. In quantum mechanics, there ends up being an uncertainty principle between the phase and the amplitude of the light, which is represented by this balloon. So if we don't apply squeezing, there's a small and equal amount of uncertainty in both of these aspects. However, if we start applying squeezing, we can diminish the uncertainty in one aspect. In this case, we're decreasing the uncertainty in the phase portion of the light. But as you can see, it's increasing the uncertainty in the amplitude. In practice, we can't reduce the total area of the uncertainty. So, but we can adjust how, where we make this trade-off. So if I squeeze instead in this direction, I can lower the amplitude uncertainty of the light at the expense of the phase. So far, as we've been using squeezing to enhance LIGO, we have been squeezing the phase of the light. This allows us to see the location of the wave and use that to measure positions more precisely. However, it has a consequence. It increases the uncertainty in the amplitude of the light. What happens in LIGO now is that because the light wave has a greater noise in its amplitude, that noise causes a force on the mirrors. You can actually think of this as the individual photons in the light bombarding the mirrors, imparting a little bit of force and rumbling them. And that rumble is at low frequencies because the mirrors are heavy. So we want to measure signals that are moving up in frequency. The ripples in space-time actually make kind of a chirp noise. Whoop. And so in order to measure at all frequencies well, we need to decrease the uncertainty in the amplitude at low frequencies and the phase for the precision of the measurement at high frequencies. So these new modifications, this new technique, what it does is at low frequencies, actually we are squeezing it in amplitude, reducing how much the light is pushing on the mirrors and reducing the uncertainty or noise from that low frequency rumble of the mirrors. And then as we go up in frequency, the squeezing uncertainty is rotating. And now at high frequencies, where we just need very high precision, we're squeezing in the phase aspect of light, and that's lowering the noise and increasing the precision. So this lets us win at all frequencies. At low frequencies, low rumble, amplitude squeezing. At high frequencies, good measurements of the light waves because of the low uncertainty in the phase. Together, this allows us to have a broadband enhancement of LIGO and measure many more signals from tiny ripples in space-time.